I think, James, you start,
Oh,
right?
profesor,
Hello,
sí,
hello, how are you?
ah,
Uh, yes, in 1 minute you can start.
ya, profesor. Envío,
Sí, que sí, ya puedes hacer el en vivo, James. Es lo que te
ya,
está
Yes,
ok,
diciendo el profe.
yes,
ok,
you can start.
unos segundos.
Okay, you can start. Karim, just 1 minute because there is a delay, and then I introduce you, okay?
Okay. The screen already shared, correct?
Yes, you can put in full mode,
Okay.
and just a second because I will introduce you first.
Okay.
Did you start, James?
No, professor, in here, then, appear that
Okay.
live. Now, yes. Now you could start, professor.
Listo, profesor.
Okay. Good morning, everybody. This is the Latin American Network for Condensed Matter. This is a network including several countries in Latin America, including Brazil, Peru, Colombia, Mexico, Chile, Venezuela, Argentina. And today's talk is presented by Abdul Karim Amirov from Russia. And Abdul Karim has a career path. His undergraduation and graduation was in Russia. Please, Karim, correct me if I'm wrong. And he has several visiting experience in Czech Republic, Germany, Belarus, and his fields of expertise is magnetic materials, multiferroic materials, and other related materials in experimental field. Nowadays he's the principal investigator in the National University of Science and Technology in Moscow. And Karim, thanks for the acceptance of this to present this talk for us here in Latin America, this online presentation. And we are ready when you are ready. Please go ahead.
Hello, everyone. Thanks again to Mario for my introducing to inviting to give a talk. My talk will be devoted to unusual application of magnetic materials, the materials called magnetocaloric materials. Mostly my talk will be devoted to my current project, to my current research, and I give some outcomes, some futures, and some reference work how these research in such advances of magnetocaloric materials for biomedicine can be developed. First of all, let's give some introductional parts. Smart materials, it's a term which connect materials that extremely change properties with one nature when you applied external fit which has another nature. For example, its table demonstrates, for example, type of smart materials. In the case of piezoelectric, force input field is mechanical. When you apply mechanical fields, its change its electric properties like potential difference appear. And other example of magnetostrictional materials, for example, when you apply magnetic fields, it's deformate and its shape, its volume is changes. It's some examples. From this point of view, the magnetocaloric materials also can be referred to smart materials. Why? I will some words about smart materials and biomedicine. There is great potential in application of in biomedicine. There are other forms of fabrication of smart materials. They mostly use particles like core shell structures, nanogels, magnetic nanoparticles with covered some polymers, and it has different stimuli triggers like as thermal response, the photo response, magnetic response, and electric, and we can combine how to control the properties of magnetic of smart materials. And coming to magnetocaloric materials, magnetocaloric effect, it's concluded is change of temperature of magnetic materials in when it's placed in adiabatic condition, or isotherm change when it's in isothermal condition, when a magnetic field applied or removed. And it's mostly prominent in temperature close to phase transition. And the magnetic caloric effect may be as positive when you apply magnetic field, material is heated, and when you it's usually called positive, and maybe also inversive magnetic caloric effect when you apply magnetic fields, materials is cooled. And mostly magnetic caloric materials is famous due they prospective in application of new type of magnetic refrigeration system. They more ecologically safely, they more efficient, and last 20 maybe more than 20 years. Many researchers in all worlds in research the magnetic caloric materials. They research new alloys and try to search. There are many prototype already constructed. So the idea which is presented in our talk is some about an unconventional application of magnetic caloric effect. If we compare the magnetocaloric effects with table which describe it with last table, input effect here is magnetic field and output is heat, which can be emitted or absorbed when you apply or remove magnetic field. And the idea is concluded to apply in biomedical application these temperature changes. And it's not so easy. It's complicated task. And from this table, you can see some advances magnetic caloric materials. And iron rhodium has record values of adiabatic temperature changes. And from these tables, we need to check to take the materials which are can be used for biomedicine, which are the key parameters how magnetocaloric materials can be used in biomedicine. First, it's the biocompatibility. It's the first main point. And second reason is temperature should be close to physiological temperatures. And second, it should have large magnetic caloric effects. No, maybe 2 Kelvin, 2 Kelvin per Tesla. If we this selected area show which materials can be used in biomedicine. I mean the temperature region and magnetocaloric effect, but unfortunately the most magnetocaloric materials, they are toxic it contains the toxic elements, and not so many materials have biocompatibility. From this point of view, we check literature, and more it have some advances in application of iron rhodium alloy. Going to the first idea for drug release from smart implants was stated by Tishan who working in magnetocaloric materials. And idea was to use the heat absorbed or released, absorbed or emitted heat to drug release. And in this, the one of the idea, the iron rhodium, this material has negative magnetocaloric effects. It's cooled when you magnetic field applied. And it's covered by a special thermo-responsive polymer. You coated implant you incorporated the drug covering by drug solution. The drug is sorbed, and when you apply magnetic field, it's cooled down, and the drug release is happening. It's just idea, and nobody know in situ regime, nobody proof of this concept, and we was motivated to in real time to demonstrate that it is working. So going to iron rhodium, why iron rhodium is interesting. First, it says the record values of magnetocaloric effects between 4 and 6 Kelvin per Tesla. It's available in commercial MRI tomograph. The second point is temperature phase transition. It's close to physiological temperature between 30-40 Celsius. The third key parameters, it's temperature, and parameters can be controlled by heat treatment, annealing, by pressure, by magnetic field. First, it has sharp changes in magnetization, and it has ferromagnetic transition in heating protocol. And its structure, when it's heating, is not symmetry is not changing, just its cubic structure just expand per 1%, and symmetry is not changing. Why it's interesting? It's also called metamagnetic phase transition. It has also low toxicity. It's in preliminary biological tests, it show low toxicity because iron rhodium, it's metal from a noble group, which already used in medical application. So, as I note that iron rhodium has giant change of magnetization around phase transition temperature, which close to physiological temperature. Second point, it's the temperature, the phase transition parameters like hysteresis, where it's that the temperature of transition can be tuned by annealing, by chemical doping, and it's more controllable than in ternary alloys. About polymer, which can be used as drug container, we consider the polyisopropylalkylamide. It's special temperature. It exhibits low critical solution temperature in aqueous solution. What does it mean? It means when you heat, it's up to above 32 Celsius, it undergoes transition from swollen hydrated states and wrinkled dehydrated state, and losing about 90% of its volume. And on the right picture, you can see how its transparency is changing, how its volume is changing. It's close to 100% change its volume. And what it means when you apply heat induced in result of magnetocaloric effect, you can change its properties. It's very interesting. And the good news that it's the PNIPAM already used in biomedical application, like in spatial smart scaffold, thermoresponsive scaffold, in tissue engineering, in regenerative medicine. It's also used, and it's well known model thermoresponsive polymers that's used in medicine. And as drug model, we use doxorubicin. Doxorubicin is a cheap, well-known drug which used for cancer treatment, and it can be easily detected using ultraviolet visual spectroscopy, and it's usually used in some biomedical tests. And firstly, we was motivated in proof of concepts, and we use gadolinium. Gadolinium is simple classical magnetocaloric effects or magnetocaloric materials which demonstrate positive magnetocaloric effects. And on left figure, you can see its magnetocaloric effect measurements. As you see, its temperature changes up to more than 10 Kelvin when your 8 Tesla is applied. Why we use 8 Tesla? It's just for proof of concept, and it's usual laboratory superconductive magnets. And as you can see on figure, we construct spatial experimental insert. We put camera spatial to in situ demonstration how its transparency, its chemical its properties is changed when you magnetic field apply or removed. So we construct the setup for in situ observation of changing of PNIPAM, of thermoresponsive polymer properties. For this aim, we fabricate this composite on figure A. It's polymer layer coated on substrates from gadolinium. As you can see, the thickness of gadolinium is more than half of millimeter, and the thickness of PNIPAM layer is about 100 micrometer. It's as you can see, the figure on the right side, it's AB, it's reference. You in here you just heating without field. As you can see, the transparency is changing. A is in hydrated state and B in dehydrated state. And as you can see, that transparency is changing. And then we apply magnetic field. The polymer is heating. It's go in result of magnetocaloric effect. It's go to dehydrated state, and it's coming back. When you remove magnetic fields, then the reversible effect is observed. It's just as proof concept. It means that the concept is working. The magnetocaloric effect can control the properties of polymer. In development, this idea, we use iron rhodium PNIPAM composite. We construct spatial inserts, and as you can see, now we designed new heater, spatial holder for sample, and as you can see, a diabatic temperature change. It's also very good, about 6-7 Tesla in 2 Tesla magnetic field change. it's enough to converse to change polymer properties. On same image, you also can see the thickness. It's about 20 micrometer. And the same experiment in here, we have the converse effect, the inverse, because we have deal with inverse magnetocaloric effect. Apply magnetic fields, it's cooling down. So first we apply magnetic fields, and as you can see, the polymer is going to it's cooling down and going to swollen state. And when you remove magnetic field, it's going to dehydrated state. And the next slide, you can see the video. It's video captured from camera of our experimental setup. It's with comment. As you can see, you apply magnetic field. It's going to swollen state, and then you remove magnetic field. As you can see, this effect is reversible, and it can be going, you can as heat as cool down the material. As you can see, the effect is worked for iron rhodium also. And the next idea was to demonstrate the drug release. And the question was how more efficiency, such way for more efficient load of drug. And for this idea, we use the simple concept, physical concept. It was our first step. We're using laser, made some wells, some periodical structure. We modified it, and on this well we load using special blade, cover it by doxorubicin, and cover then by polymer. From this same image, you can see that not all polymer, not all surface of iron rhodium is covered by polymer, because it's due some imperfections of surface morphology after laser treatment. It's not so bad because it's closed this well by polymers, and on next stage idea was to apply magnetic field and demonstrate the doxorubicin is released. So for this task, we use we use modified this insert using this one camera, and the protocol was same, but spatially here we hold our sample in about 36 temperature, each close human temperature. Apply 3 Tesla magnetic field, not because here we use 8, but in developed version we use 3 Tesla, because 3 Tesla is available for commercial magnetic MRI tomograph sources. And as you can see, the doxorubicin is successfully released. We apply magnetic field, and the drug release is happening, and the drug release was controlled. It was releasing was detected using OF with spectroscopy and Raman spectroscopy. And OF with spectra, you can see that is yellow or orange line, it's released DOC solution. We collect it from this place. We collect it and put in OFV's spectrometer. So and making some reference measurement, we obtain that its concentration of drug is about 0.04 milligram to milliliter. And Raman spectroscopy also confirmed that drug release happens successfully. So next question was about biology. Is this material toxic? The first test shows that it's we use special GFP mouse embryonic fibroblast cells, and they was grown on control surface, and it's special biological plastic called polystyrene. And second B, it was grown on PNIPAM iron rhodium composite without drug, without doxorubicin, because it's toxic for cells. And as you can see, the cells that they're located not only on surface, it's also grown in wells, in the wells, located directly in the wells. And as you can see, the biological experiment shows its materials, it has low toxicity, but anyway, more experiments, biological experiments are needed. And we also make some image from this polymer from this composite, and as you can see, the fibroblasts fill wells, they attach it as on polymer, it's figure A, and as well on metallic place of iron rhodium, because as I note, that polymer is not fully covered the surface of metallic substrates due to the imperfectness of wells after laser treatment. So what it means? It means that preliminary, it's the material show good biological results, and so this idea can be developed in future. And about research by one file, by one picture, and firstly we made some wells using laser radiation, load doxorubicin, not covered by PNIPAM, and when apply magnetic field, the material is cooling down due a magnetocaloric effect. It's cooled down polymer, converse polymer, the phase transition happens, and it release a drug. It release a drug, and so it also show good biocompatibility. It show and good adhesion of cell on the surface of PNIPAM, on the surface of PNIPAM and iron rhodium, and the results they are published. It was just recently published on this journal, and the video you can see on the site as supplementary information. So we also have a plan to develop this approach, and it will be aim of future raise of our project. So where else can be used magnetocaloric effect, and it also can be used in MRI as MRI label, And this idea was proposed and released just a proof of concept by colleagues from USA. You can see the ref to the work. And as you can see, the idea was followed. Iron rhodium has just sharp change of magnetization. It can be controlled by magnetic field and by temperature. It also depends of composition of materials, and they put the iron rhodium material in special insert and put in MRI scanner field and detect its MRI signal. And in antiferromagnetic states, it show low signal. You hit it and do a ferromagnetic phase transition. Its magnetization is extremely changed, and you can see the increasing on, as you see on figure A, and in here as a figure A is the signal, the MRI from signal is increasing. And also when you're cooling down the materials, its signal is decreased. And it can be realized using different strategy. It depends on also from magnetic field, because magnetic fields shift phase transition temperature close low temperature region. It also can be tuned by temperature, where it can be realized in future. In future, it can be realized as prospective MRI. If it work in particles, it's this effect was shown on bulk. If it works on particles, it's very good new because you can construct special MRI labels with switch on mechanism, switch on approach. So what does it mean? It means when human temperature is increased, the label is worked. You can see the changed the signal from MRI signal from particle. The colleagues continue this work, and they show that it also works in micro scale. And here you can see they are using lithography. They prepare some. They grow some films with different squareness, and as you can see, its contrast is also changed. Its contrast depends from size, from area of these particles, and in micro scale, it just was reported this work, and they show that it also can be worked in micro scale, but here is not particles, and it's special like island, like film on substrate. It's epitaxically grown structures. It's not particle, but it's good news because in micro scale it's also work. As you can see, it's magnetic force microscopy. It has domain structures, and it's by heating and cooling down you can control it. So on next slide in here, our idea of our project on development. The first, here we demonstrate that it's worked in that is worked in bulk. First, it's our working package one. We synthesize, we demonstrate that is work, and we can conclude that controllable drug release using magnetocaloric effect, it works. The second point, and now we synthesized some particles in microscale by approach up-down. It's mechanical milling and laser ablation, and down-up when you use solid some chemical methods, for example, solid state reaction methods, and we research its magnetic properties, magnetic magnetic caloric effects in micro scale. And then in next, where it can be used. It can be used also if we observe the large magnetocaloric effects. It also can be used as a spatial smart gel, where due a negative magnetocaloric effect, you can release in drug and for other application. And in nanoscale, maybe its effect will not work in the nanoscale, but if we observe the sharp phase transition, maybe it can be used in MRI as MRI label. So we also search new opportunities where it can be, this effect where it can be used. And here on next slide, it's also some picture which was drawn with me and my child. And in here, it was our ideas where can be used iron rhodium. Why? In conclusion, just iron rhodium demonstrates the good opportunities in application for biomedicine. Maybe other alloy from this metal from noble group also can be used. But our preliminary experiments with gadolinium is showed that its material is toxic. It cannot be used in biomedicine. So finally, in biomedicine can be the question, the point, magnetical effect can be used in biomedicine. Firstly, we use the heat. It's direct, it's smart effect. Heat emitted or absorbed when your magnetic field apply or remove. And second, it's sharp phase transition. It's sharp changing of magnetocaloric effect. It can be it's during phase transition. It also can be used as switchable, as switch on option for MRI label. Also, we search for new opportunities where can it be used. Maybe it's used as in particles, microparticles. Maybe it can be used in a spatial ribbons on micro scale. So we are searching for new opportunities of application of magnetic caloric materials. So thank you for attention. Question?
Falta luz, né? Não é que eu estou fazendo o giro.
Karim, thank you for your presentation. I will open for the panelists for questions. Following the order that appears for me in this list here, Gabriela from Argentina, do you have some questions to address to Karim?
No. I would like to know which is the structure of this iron rhodium. It's a cubic. I guess.
Yes. Its work is just in cubic in alpha phase. In gamma phase, it's not working.
Okay. And can you put some other element as a defect, like a noble metal, platinum or palladium, to change the temperature of the transition?
Yes. It's can be used for tuning of transition temperature without decreasing of magnetic caloric effect. Yes, it can be used maybe cobalt, nickel, and other elements, maybe palladium, maybe can be used. But we have synthesized these materials and we are working on it.
Okay. And did you compare with some calculations to see the electronic structure?
We just compare the work, calculated works of our colleagues, and for calculation we open for collaboration because we mostly work it as experimentator, and for predicting of new structures we open for collaboration.
Right. Well, in our group we do DFT calculations and also some molecular
It's good
dynamics.
opportunity. DFT, it's in the next text is also to working with phase diagram of iron rhodium,
Yeah.
and it's very interesting for us to predict its phase diagram.
It's a very interesting system.
So we open for collaboration.
Okay. We too. Okay, thank you for your talk. Very, very interesting. The physics and the application, both. It has both sides of interest.
Yes, it's some a little bit unusually because we change our ways from refrigeration because, as you know, iron rhodium it's very expensive for refrigeration, and the idea was where can it be used, and the polymer has low mass, and why that the efficiency you can converse its properties. As you can see, the thickness is of polymer is very small.
You put the polymer on top of the metal.
Yes.
That would be
yes, I use iron rhodium as plate as substrate.
Yeah. Okay. Thank you very much.
Okay, thank you, Gabriela, for your questions. Mauro Doria from Brazil, do you have any questions to Karim? Mauro, your mic is turned off.
No, I just would like to thank him for this very illustrative presentation. I learned a lot, but I don't have any technical question about it. Thank you.
Okay, thank you, Mauro. Isaías, do you have any questions? I think Isaías is have problems with the connections. He left. Okay.
No, I'm here now.
You are here. Okay,
Yeah.
you are not appearing to me
There
here.
was a blackout here.
Okay, you are here. Okay. Do you have any questions, Isaías?
Yeah, I just want. Thank you, Karim, for your good talk. I would like to know if you have worked with superconductors in in case of the magnetocaloric measurements, or if you know other groups that are working with superconductors in magnetocaloric effects.
The question was about magnetic field source, yes?
Magnetocaloric effect using any kind of superconductors.
In kind of superconductors. Sorry, Mario, the question, what about, what question? About, Mario,
let me help. His question is if you know someone, if you know someone measuring magnetocaloric effects in superconductors.
Yes, we measure in our experiment. We use a Tesla laboratory superconductive source. Why I told about 3 Tesla? We specially use 3 Tesla because it's available in medical tomograph.
Sorry, Karim. Not the source of the fields, but the material, as the magnetocaloric, as the magnetocaloric material as a superconductor.
A superconductor, I didn't research it.
Instead of iron rhodium superconductor.
Instead, oh, it's a good idea. For example, which one? It's barium ceramics or oxide ceramics. Which one you can propose?
No, my idea is study the dynamic of vortex using this technique, magnetocaloric effect. It's my idea.
The idea of using of superconductive materials for magnetocaloric effect. Yes.
Sure.
Oh, it's new opportunities. It's new. I didn't research this approach, but maybe it will be interesting in future. But I didn't research caloric effects in superconductive materials.
Thank you very much, Karim.
I hope that I correctly understand, Mario.
Yes, yes. Is that correct, Isaias?
Yeah.
But I'm thinking about which one material from superconducting can be used. I mean, theoretically, which one? Just high temperature superconductive materials.
Uh, and my idea is use any kind of superconductor since it is type 2 superconductor because I would like to see penetration of vortex and exit of vortex and how it contributes to magnetocaloric effects.
No interest.
No, include or excluding type 2?
Includes.
Oh,
There is vortex only in type 2.
Okay.
thank you.
Oh, thank you very much, Professor Karim.
Oh,
Gracias,
thank
Márcio.
you.
Mário.
Okay. Thank you, Isaias. Edgardo, do you have some questions?
The question is the type of tissue, yes? Oh, we because with physics we just proving of model as a proof of concept, and why we use doxorubicin because it was cheap, cheap drug and can be easily detected. It's all is model experiments and. For to answer your question, we need to collaborate more hardly with biologists or with medicals, and that our next idea was to check is it working in micro scale. It's very interesting because is it safe? We already synthesized the particles, microparticles, and idea is it work in micro scale that we can be realized as gel, spatial gel, because it's complicated to realize to put bulk into human. It's very complicated and it's just a proof of model, and we just demonstrate that the idea is working, and in future, of course, we need to correct our plan. It's our future. It's our plan for future. Yes, but we focused not only drug delivery, which also can be used in in other application. and not also in drug delivery. The other idea also is using special laboratory device, special for tissue engineering, and you pull down the polymer, and you can deattach the stomal stem, special growth stem. You can deattach, and it's also used with the special surface with changed with convertible surfaces, but it's not idea is not focused on drug release. The drug release we use as just as one concept. It can demonstrate the possible opportunities application of magnetocaloric effect. And in here we're working just as physics and engineering, and of course it's in future it should be corrected in our plan. Yes, now we're also working with colleagues to use a different kind of polymers too. Yes, with different temperature. For example, not sorted through the temperature upper close to human temperature, 36, 37, and now we are also working with changing the temperature of polymer too, and the synthesis of new type of polymers. And in our idea, all was model, and PNIPAM polymer, doxorubicin, and aeromrhodium, it all was used as model objects.
Thank you, Edgardo. As a follow-up from the Edgardo's question, I know, Karim, that people in Moscow, Vladimir and Tichin group, they can do some clinical trials with rats and in these kinds of experiments to try these materials. Did you try these clinical trials to see if in fact your materials are efficient to be used in
On second
rats, for
year,
example?
on this year, we are planning to make some experiment on laboratory mouses using laboratory mouse using the laboratory MRI source in 3 Tesla. Now we are focused on this research.
Okay, good.
We are planning this experiment.
Okay. Okay. James, Ximena, are the students have some question? No, I think no. To conclude, I think all of the panelists already gave their questions and opinion. Karim, do you have can you give your final words to conclude the talk from today?
Also, I would like to thanks also the question, then the ideas for using of superconductive materials. It was also very interesting. The idea about some biomedical aspects also was interesting. The question about calculation, DFT calculation. I am glad to this question, and I open in new opportunities for collaboration with you. And thanks you, Mario, that you invite me and give me the opportunity to give this talk. And sorry that it mostly was focused in my project, but mostly I demonstrate my experiments. But it was a very pleasure for me.
Okay, thank you. No, that's the idea, to present what you are doing and to share the idea with us. Thank you, Karim, again. And let's open our camera to say goodbye.
Goodbye.
And thank you, Karim, and all of the panelists for to be present today here. Bye bye, and have a good weekend.
Bye-bye.
Thank you very much. We will contact you.
See
Bye bye.
you, Karim.
Thank you.
Bye bye.
Thank you.
Bye
Thank
bye.
you.
Bye bye.
Hasta luego a todos.